Here's Pre-Calc lecture 10.1.3. It's about hyperbolas. It says, imagine mathematicians studying the conic sections before their equations were known. They had just finished studying the ellipse, which has to do with the sum of distances. Now they are curious about what will happen if instead of considering a sum of distances, they will consider a difference of distances. They wonder what curve will result from the set of points where the difference of the distances from two fixed points to any point on the curve remains constant. A hyperbola is the set of all points in a plane such that the difference of the distances between two fixed points, called the foci, to the curve is constant. So I'm going to remind you what we learned about the ellipse. We just did the ellipse in our last lecture, and I even had that thing made out of string, and we found out that this distance plus this distance anywhere around the ellipse is a constant, and the constant is actually 2 times a, by the way. Well, it turns out that and here's the equation of the ellipse. See the difference between the equations? There's no difference at all, except for that the hyperbola has a minus sign and the ellipse has a plus sign. But the definition of a hyperbola is that this d1 minus d2 is actually equal to 2a, and we'll go over that a little bit in a minute. So anywhere I put a point, even if it's down here, this distance, take away this distance, is a fixed distance, which is 2a. So there's my hyperbola. And then your book likes to start out with having you just look at some graphs of hyperbolas. So it wanted you to graph these 3 hyperbolas. And it wanted you to do it like without really knowing how they work yet, just so you could explore them. And it was saying you could use some strategies, like you could find the maybe some intercepts and things like that. I'm going to go ahead and spill the beans and just show you how to graph them. But it is true that you could find the intercepts, like you could put in 0 for x, and actually, what would happen if you put in 0 for x and try to find the y-intercept? Well, you could divide both or multiply both sides by -1, and then you could multiply, or just maybe multiply both sides by -16, and then you would find square root of -16. But you can't have a square root of a negative number, so that tells you something about the parabola, and we'll talk a little bit more about, sorry, it's not a parabola, the hyperbola. We'll talk more about that later, but basically there's not going to be a y-intercept. Sorry, yeah, a y-intercept. So when I let y equal 0, if I let y equal 0, here I'm covering it up because I'm pretending it equals 0, and I multiply both sides by 100, then I would find that the x-intercept is the square root of 100. Well, that's just 10. So that they wanted you to do these problems just with that kind of thinking and maybe plug in some numbers in and whatnot. But I'm kind of going to do it a little bit faster here. So if I had to graph this, I would draw my xy graph. And then I look at my equation. I got x minus h and y minus k. So that gives me my center. In this case, my center is just going to be at the origin. And then I look at a and b. That's a squared and that's b squared. So the square root of a is 10. So I'm going to go right and left by 10. And I'm doing that on the x-axis because that's underneath the x. And then on the y-axis, I'm going to go up and down by 4 because that's the square root of 16. This is y, this is x. And I know this sounds weird, but I'm going to make a box. The box is not part of the graph. It's just an aid in graphing. I'm going to connect the corners. I had a straight edge, but I remember I put it in a drawer. It was so clever. I put it away in a drawer, and now it's not handy for me to use. There we go. So we said this thing can't have a y-intercept, but it's going to have x-intercepts. So here's my x-intercepts, plus or minus 10. And if these are asymptotes, really I should have made them dotted lines. Sorry about that. That would have been even more challenging to make them as dotted lines. It's going to go like this. It's going to have these two branches that go like that. Okay, and that's basically essentially the graph. There's going to be foci, so my graph's supposed to go right through the x-intercept. There's going to be a little foci on the inside of both of them, and we'll talk more about that later. But let's just do a couple more so you can see. Letter B, it said y squared minus 2 over 49. Y squared minus 2 over 49. So y minus 2. So y minus 2 squared. So this is h and k. It's going to be 2 and negative 6. So I'm going to go, that's my center. And then a is, notice that's underneath the y. So that's actually going to tell me to go up and down by 7 from my center. So I think this was 6. Up by 7 and down by 7. And then I'm supposed to go, it told me 36, so the square root of 36 is 6. So I'm going to go right and left by 6. And left by 6. 1, 2, 3, 4, 5, 6. And I'm going to, it looks horrible. They're supposed to be lined up. Let's make it bigger. There we go. So I'm going to make myself a graphing aid. And now this one cannot have x-intercepts. It's only going to have y-intercepts. So that means it's, oh boy. I'll try to make a straight dotted line. It's going to have only y-intercepts, not x-intercepts though. So it's going to look a little bit like that. Okay, and there it is right here. Okay, and then I don't think I'm going to do the next one because it just takes so long. But the next one, I'll just kind of show it to you. So the center would be at 1, negative 7. And then the little box that you make would be 3 to the right and left, and 2 to, up and down, and then it would, they don't show it, they scaled it kind of funny, and then you would connect to the corners and you would graph it, and that is how you graph them. So the graphs, at least you have a feeling for what these graphs are going to look like. In part 2, we're going to explore eccentricity and a few other things.